dark openings may very well be one of the generally interesting and puzzling peculiarities in the universe. They are gigantic monsters concerning power, however, at a similar time, essentially undetectable to us. Like a dark opening weighing maybe 2 to 4 million times the mass of the Sun. As a result of the exploration that was put into them over the last several many years, we've gone from knowing literally nothing about them to getting to find out increasingly more very close and individual. While things have recently gotten more insane, Kaku recently reported that we at long last got to take a gander at what's inside a dark hole. This new data brings light to the subtleties the universe of science could have missed from the beginning. Join us as we dig further into dark openings and divulge what's inside. Space is enormous and awful. Before we dive into the subtleties of what Kaku found, we need to discuss the firsts. Despite the fact that a large portion of us have some idea what dark openings are, there's still a few holes in the right data. You see, in 1916, Albert Einstein published his hypothesis of general relativity, which anticipated the presence of dark openings. Around then, the concept of dark openings was absolutely hypothetical. It took another 50 years for established researchers to find proof that dark openings in fact exist. This occurred during the 1960s. They were studying the Cygnus star grouping when they saw a strangely radiant blue star that was discharging X-rays. This star was certainly not a stale object, but was going around a monster dark something. Upon further examination, it was viewed that the X-rays weren't just moving around on their own. They were being sucked into the dark thing they were circling. Hence, the name dark opening. This revelation was critical because it gave evidence that dark openings really exist and that they were not just an invention of Albert Einstein's wild imagination. While that was extraordinary, it also meant that there was this stunning substance in space that we desperately had to find out about. So, analysts from one side of the planet to the other got to work. This dark opening was named Cygnus X1, and it is situated in the star grouping Cygnus, around 6,000 light-years from Earth. It was no small revelation. It's multiple times more brilliant than the Sun and inconceivably thick, which makes it have a strong gravitational draw. The gravitational draw is so strong that not even light can escape it. Therefore, it is known as a dark opening. The idea of a dark opening is both captivating and frightening. It is a district of space where gravity is so solid that nothing, not even light, can escape. Whatever gets excessively near a dark opening will be pulled into it, gone forever. Yet, that aspect of peril makes it considerably more fundamental to learn all that there is to be aware of them. Was this it? Or were we just starting? The response turned out to be the last option. After the discovery of Cygnus X1, researchers began to look for other dark openings. They found that there might be near north of 100 million dark openings in the Milky Way alone. But since they are so unbelievably difficult to identify, we still try not to have a definite number. All things considered, from the vibes of it, there are a few million dark openings in the Milky Way and our very universe, which is what makes them considerably more essential to study. So how about we break it down? The principal concern with dark openings is always going to be gravity. Their gravitational force is so extreme that anything that enters it packs down cosmically until it turns into a peculiarity. In more straightforward terms, dark openings are like infinite vacuum cleaners that suck everything in. One of the most alarming parts about the examination that has gone into dark openings is the reality that if somebody somehow happened to fall into one, they would come to the point where they become a solitary line. This interaction would happen gradually, and the individual would pass on before the final structure in reality sets in. So, let's just say that nobody should step into one, but they're everywhere. So, might we at any point truly be in peril? Regardless of the way that the nearest dark opening to Earth is 500 to 1,000 light-years away, it's still close enough to raise questions and concerns. In 2021, researchers had the option to deliver the first clear photo of a dark opening, specifically the M87 dark opening. This dark opening was shot over several nights, and with each photo, the analysts gathered more and more proof about it. They needed to line the individual photographs together to make something that filled all the gaps. This way, they had the option to sort out that there are 3 layers to a dark opening. It's not only one single expanding opening of nothingness, as many people believe. Things are significantly more convoluted than that. To even get to the nothingness part of a dark opening, you need to make it through the first two layers. The first layer is known as the event horizon, which, while in the first layer, is the point of no return. Once you pass the event horizon, there's no option but to press onward, and you will be sucked into the dark opening. It just deteriorates from that point forward. The second layer is the photon sphere, which is the region where light circles the dark opening. Any light that enters this area will be caught and won't be able to escape the dark opening's gravitational force. Finally, we come to the third layer, which is the singularity. This is where all that enters the dark opening gets packed down cosmically until it turns into a singularity. The singularity is a point in space-time where the laws of physics, as we know them, break down and we just can't predict what happens next. At the singularity, the density is infinite, and the laws of physics, as we know them, cease to exist. Now, what makes all of this vastly more terrible is the fact that each and every dark opening you study will be totally different from the last. Sure, they do tend to follow the same three-layer concept, but the way they function could be unfathomably different. At this point, if this were anything else, all we really need to do is bounce back on those telescopes and just concentrate on the central issue in detail. But with dark openings, you can't really do that. Researchers can study dark openings indirectly by noticing the radiation they discharge and the gas and dust that surrounds them. Sending a probe like the Voyager inside a dark opening is absurd, since whatever enters the event horizon is pulled toward the singularity, where it is packed to a limitlessly small point. So, you can't exactly waste billions of dollars just to get a glimpse like clockwork, because the second the probe gets close enough, it'll simply smash into nothingness. As a result of that obvious issue, researchers are left with no choice but to study these objects in a two-dimensional way, despite the fact that they are three-dimensional singularities in reality. To make matters even more challenging, there are also the two problems of each dark opening being unique and the laws of physics as we know them breaking down when we try to investigate within. This means that the traditional methods of scientific inquiry don't actually apply to the study of dark openings. That doesn't mean the scientists haven't been busy. There are plenty of different theories and explanations of dark openings, and with each one, things get more and more interesting. One of the most compelling theories about the formation of dark openings is that they are made from falling stars. When a star all depletes its fuel, it can no longer produce sufficient energy to balance the power of gravity that is constantly pulling inward. Therefore, the star begins to fall in on itself, shrinking and becoming denser. If the star is large enough, this process can continue until it turns into a singularity. To grasp the concept of dark openings top to bottom, NASA researchers turned their attention to the center of the galaxy, M87. Cosmologists noticed a strong whirlpool of very hot hydrogen gas that was spinning at a surprising pace of 1.2 million miles per hour. The sheer power of the spinning disk of gas should have caused it to fly apart in all directions, yet it didn't. Researchers found that there must be a huge mass aggregated at the center of the galaxy to keep this from happening. This massive object weighed as much as 2 to 3 billion suns and had to be a dark opening. But that doesn't seem to be the only theory where dark openings twist. In 1963, New Zealand mathematician Roy Kerr used Einstein's equations of gravity to give the best description of a spinning dark opening. He showed that a spinning dark opening wouldn't implode into a point as previously thought, but into a ring of fire or a thin disk. The disk would spin so quickly that radial forces would keep it from collapsing. This spinning disk of matter is known as the ergosphere, and it is the region surrounding the dark opening where the laws of physics begin to break down. However, the most interesting aspect of Kerr's solution was that it predicted the presence of an Einstein-Rosen bridge, also known as a wormhole. This hypothetical passage through space-time could connect two separate regions of the universe or even two parallel universes. The idea is that if one were to fall into a dark opening, instead of being crushed to oblivion, one would be sucked down a passage through the ring of fire and shot out a white hole in a parallel universe. To understand how this works, we need to look at the concept of spacetime in Einstein's theory. Spacetime is the fabric of the universe where objects with mass bend this fabric, creating a gravitational field that causes other objects to move toward them. Now imagine a piece of paper, representing spacetime. If you place 2 points on the paper and draw a line between them, this is a representation of how objects travel through spacetime. But what if you could fold the paper in half and create a shortcut between the 2 points? This is the basic idea behind a wormhole, a shortcut through space-time that connects 2 distant points in an instant. Wormholes aren't just a science fiction idea. They are actually a prediction of general relativity, although no one has ever observed one directly. The reason is that wormholes are inherently unstable and would collapse almost immediately. Yet the existence of an Einstein-Rosen bridge would mean that dark openings are not just enormous vacuum cleaners, but could also be gateways to different regions of space-time. So, could we use a wormhole to travel through space and time? Unfortunately, the answer is probably no. Even if we could stabilize a wormhole, it's unlikely we could use it to travel faster than light. Einstein's theory of special relativity predicts that the speed of light is an absolute limit on how fast anything can travel through space-time. However, even so, the theory of wormholes and dark openings as pathways to other parts of the universe or even to different times has been a subject of interest and speculation among physicists for a long time. The possibility that there may be shortcuts through the fabric of space-time, allowing travel over vast distances or even into the past, could be revolutionary if we could ever achieve it. One of the most captivating ideas in this area of study is the CER wormhole, named after mathematician Roy Kerr, who first described it using Einstein's equations of gravity. This kind of wormhole is essentially a theoretical tunnel through space-time that could connect 2 distant points, like 2 different universes or even 2 different times within the same universe. The Mutt wormhole is often pictured as a ring-shaped entrance, like the mirror in the story of Alice in Wonderland. Walking through the looking glass transported Alice to a reality where creatures spoke in riddles and logic didn't always apply. Similarly, going through the Mutt ring could potentially transport an explorer to another universe or some other time where the laws of physics might be very different from those we are familiar with. But at the destination, it could just be ordinary. While the possibility of wormholes for interstellar travel or time travel is certainly exciting, as we've seen before, it's also a topic of debate and discussion among physicists. Some have pointed out that wormholes, especially Mutt wormholes, may be unstable or difficult to cross due to the intense radiation and subatomic forces surrounding their entrance. Critics argue that Einstein's equations of gravity, which are used to describe wormholes and dark openings, only work for gravity and not for the quantum forces that govern radiation and subatomic particles. To truly understand the concept of these peculiarities, a new theory is needed to unify the laws of gravity with a quantum theory of radiation. Throughout the universe of science, this is known as a theory of everything, a single theory that can unify both Einstein's theory of gravity and quantum theory. Michio Kaku, a renowned theoretical physicist, has been working on a theory of everything for a long time, but there are many different versions of what this could be. The only one that has shown promise is superstring theory. Superstring theory unites gravity with a theory of radiation. The theory suggests that subatomic particles are really tiny vibrating strings, and that the universe is an orchestra of these strings. Just as different musical notes correspond to different vibrations of a violin string, different particles in nature correspond to different vibrations of a superstring. One of the fascinating things about superstring theory is that as a string moves in time, it bends the fabric of space around it, creating dark openings, wormholes, and other exotic solutions to Einstein's equations. This actually means that superstring theory not only unifies Einstein's theory of gravity with quantum theory, but also explains many of the strange phenomena we observe in the universe. However, there's something about this theory that really throws a wrench into how simple it might have seemed at first, but in a way makes more sense too. Superstring theory requires 10 dimensions of spacetime for the strings to vibrate. This is very different from the 3 dimensions of space and 1 dimension of time that we experience in our daily lives. It's hard to imagine what these extra dimensions might be like, but physicists have developed some plausible models that can help us understand. Consider a 2-dimensional lake inhabited by fish that are only aware of the dimensions of length and width. To these fish, there is no such thing as height, and they can't even imagine what it might be like to live in a 3-dimensional world.